Hello and welcome to another Harwell XPS look at curve fitting. Today we're going to be looking at some peak modeling. We've already gone over backgrounds in a previous video, so now we're just going to be looking at how do we add peaks, what kind of peaks can we add, where might we want to use different peaks, that kind of thing, and some of the other parameter controls that curve fitting has got within the software. So got a couple of examples, so let's get going. Okay, so I've just loaded up my sample. So this is just a polymer sample with some calcium in it. We're going to be going through the basics of how we start a peak model. So as we saw in a previous video, our peak fitting box is up here. We've got the mini version and the full version. We can use either. We'll start with the mini for now because we don't need too many options for the carbon. It's pretty straightforward. I'm going to go with a smart background. As we said in the previous video, there's not really much difference between this and a Shirley background, so we'll just kick things off by adding in a background now. It isn't really that much different to a linear background, to be honest, as is the way with carbon. Yes, we've got a couple of options here. You've got an SGL, so the sum of a Gaussian lengths. We've got a void type function and an LA function. As you might be familiar if you've used CAS or XPS in the past. Realistically, you're probably not going to see a massive difference between these. That might be controversial to some, but they're all going to give you more or less the same answer, particularly if you're looking at quite simple systems like this, carbon, for example. So I'm just going to go for an LA because that's what I tend to use the most. And I'm just going to add single peak. So this is our first peak in here. We've quite clearly got two species, so I'm just going to go ahead and add a second peak straight away. If we add too many peaks, so for example I stick another one in and think actually I've probably not got that many, you can always click on the remove last peak function. But for now we can just click on fit and see what this does. Straight away that looks a really nice fit. It's lining up with the data very nicely. If you look at the residual down the bottom, we've got a very nice fit to the data, residual standard deviation of about 2. So I mean already this is looking very nice. But what we can do is to look at some of our controls up here and think about how we might use some of those to constrain this fit to make it more realistic. Now the full width maximum we've got here, if we look at our two boxes, so I'm just going to go ahead and change the name of this. So this is our first peak is the peak in blue. You can see if we click on that, it'll bring up this nice little labeling box here. So I'm just going to call this our CO. So this is a polymer, like I say, where we've got some polyethoxide and ethyl ethoxide chains within it. So we've got lots of CO ether style groups, and then we've also got some CCCH in there as well. Now the full width maximum is pretty close. I would say that's close enough that I wouldn't be particularly worried about leaving these as is. However, if you start fitting and you notice that one of them is quite a bit bigger than the other, you can put some constraints in. So same as you might find in CAS or XPS, we can just put in something like A times 1. So you can see peak A up here, we've given it the peak label CO. This is our ether groups. Say we wanted to just make sure that the full width maximum of these two peaks is the same, we can put A times 1 in, and then if we click fit again, that's now going to fit those so that the full width maximum is locked to be exactly the same. If you remember, the width of the peak is related to the core hole lifetime, as well as a number of other things, but the differentiating parameter of two XPS peaks is going to be the core hole lifetime. For something like this, where we've got carbon bonded to an oxygen versus a carbon-carbon, the lifetime of that core hole isn't going to change, so this should be the full width maximum should be pretty close to equal as it stands. When we first came in, they were almost spot on anyway, but we've just made sure that the software is telling the peak modeling to keep the width of these peaks the same. So there are some modifiers in here which relate to the properties of the peaks. So we've got kind of the width of the Gaussian and the width of the Lorentzian function within our convergence. Again, you can kind of lock these if you want. But the nice thing about curve fitting is that the software will actually kind of do a model of the optimal parameters for this as well. These do look pretty close, but again, if we just wanted to be sure that our peak model is consistent across the two peaks, we can do the same thing in the parameters of the actual line shape and just say, okay, well, we've got our full with our maximum locked. Let's also just lock the properties of these two peaks together so we're not getting wildly different shapes. Again, for a system like this, we shouldn't be seeing a particular difference in terms of the line shape. If you move on to systems where you might have something quite conductive and something non-conductive, then you're probably going to start to get differences in line shape. This is just a simple polymer. We're not going to be expecting much difference. And you can see now, if you look at these peak parameters here, they've been locked pretty closely. We can add a modifier using the hash key. If we do a times 1 hash, say 10, that's going to give us about a 10% margin of error. So if we click fit again, you'll now see that this has gone back to the original line shape parameters because we've given it that kind of grace, that margin of error, about 10%, and that'll allow this model to kind of primarily focus on fitting the data rather than on being a more realistically or physically realistic fit. So if we keep on looking there, we've then got concentration. All of the sensitivity factors for everything in curve fitting are loaded in the database, depending on what kind of data set you open. Of course, this is the same element, so it doesn't really matter. We're just kind of doing an integration based on the peak area, but you can read your concentration there. If you do build a model where you've got multiple elements, then that's when the sensitivity factors will be taken into play to calculate this concentration. So that's a nice and really simple system that you can kind of try something similar, try some carbons. We're going to have a look at some doublets now and just make sure that we're all aware of what kind of parameters we need to control and what kind of things curve fitting can do to make sure that your data is modeled to the highest standard that is possible. Okay, so I'm just going to move to my calcium, just open the sample manager up here, and I've got quite a big data set here, so it's just easier to use the sample manager rather than the drop down. And this time I'm going to move to the bigger window. So next to where we opened before, we've got mini, we've got the full peak model here. Again, I'm just going to stick to a smart background. Let's just move these around the peaks, just create a simple Shirley background. But now if we get into the peak fitting window on the kind of main window, we've got a few more options. So as well as the SGL, the LA and the Voigt that we had before, there's quite a few more options. I'm not going to go through all of them. Gwilym has very helpfully put in a little tooltip. So if you select a line shape and you just hover over this question mark, it'll bring up what that function does, where it comes from, and you can just have that as a kind of guide and a reference. You can also choose the fitting method. There are a few methods here that you just use slightly different algorithms. Again, if you're watching this, I'm kind of assuming that you're more on the beginner's side of things, so perhaps we can look at these in more detail in the future. I would say for now, it's probably not too important that we look through them. Stick with least squares and you'll generally get a pretty good fit. The convergence is basically kind of how good the fit needs to be before it stops. So the smaller this is, the better your fit needs to be. So you can put on a huge number of iterations here, and it will just keep fitting until it kind of reaches the maximum conversion, or the minimum convergence, sorry. Or you can just say, well, I only want to do 5 iterations, and then your peak fitting will be quicker, but it may not be quite as good realistically once you've got through a few iterations. Probably, unless you've got quite a complicated data set, probably your peak model is going to be looking quite good anyway. But the options are there if you want to tune your peak fitting a little bit more. So I'm just going to add 2 peaks in. So by default, KherveFitting knows to add the spin-orbit doublet of our elements. So we've got calcium 2p, and if you look at our peak labels, we've got calcium 2p 3/2, calcium 2p 1/2 already labelled. Gwilyn's even implemented an automatic doublet separation for parameter into the position, as well as your forward half maximum and your area. There should obviously be a little bit of caution with some of these. Obviously, if you have something like costochromic broadening, you're going to have to modify your forward half maximum parameter locking. But at that point, you're probably going to be a bit more aware of what you're doing anyway, so you should be picking up on these kind of things. We've got the same options as before. So if we have, for example, on our peak modifier here, we've got a plus 3.5. So this is our doublet separation between the 2 peaks. There is a hash function that allows you to do a plus or minus 0.2. In theory, the doublet separation should be fixed. In reality, sometimes differences in how your background rises mean that when you do a peak modeling like this, there can be some slight small shifts. Or if you're making a particularly complicated model, so if you, for example, if you're trying to model Auger data to speciate copper, or if you're trying to look at something like cerium, then some of the kind of the grace parameter there can be a big help in actually getting a repeatable and reliable model. But for now, we can just kind of leave this as it is. So we've just gone for an SGL here. Again, it's probably not going to make a massive difference. We could go with an LA or a GL function. SGL is probably the most straightforward. We don't really have any parameters that we need to worry about. So if we click fit n times, we can now see our peak model constraining to fit our data, and we've got a pretty much 50-50 concentration. Each of these peaks is going to have a separate relative sensitivity factor, so they should be quantifying out at about 2:1, 1:1, sorry. Even though the peak area is 2:1 because it's 2p, and that looks like it's quantifying out pretty nicely. What we can do, and just to show you the grace parameter again that I was talking about, you can modify any of these. If we just click on fit one time, and you now see that the software has maintained that peak locking parameter. And if we just give it a grace period and fit again, the software is now going to be trying to actually optimize the peak model to the data. So like I say, there's something that's probably more useful in some more advanced fits, but it's nice to have that option as well anyway. If we wanted to fit something more complicated with multiple doublets, you can still use the same process that you might use in something like XPS, where you kind of lock all of the peaks to a single peak. So for example, if you wanted to add a second set of doublets and lock the forward half maximum all to peak A in this case, you can absolutely do that. Of course, again, if you're looking at something like a metal versus an oxide, this is probably not too sensible because you should have different line widths due to the different core hole lifetimes. But again, all of these parameters should be quite familiar if you've ever used Casper XPS or Avantage to do your data analysis, and they're pretty straightforward here. So that's it. So the doublet fitting is pretty much the same as the kind of the standard single peak fitting. You've just got this kind of extra set of parameters to deal with, but again, KherveFitting does put in very good defaults, so you shouldn't have too many problems as long as you're using the two peak doublet function. So we've got one more example to look at now, and we're going to be looking at a bit of an asymmetric peak. So some of the more complicated line shapes within KherveFitting. Okay, so I've got another example here that I quite like. It's nickel metal, and it's quite nice because you've got that peak asymmetry, but there's also a couple of extra things going on. So I'm just going to draw my background. I'm only going to fit the 2p3/2 for this. We could do the same for the doublet, but it's basically following the same rules that we did in the previous one for all of our peaks. I think we can just fit a single peak here. So I'm just going to create a region. This gives us a Shirley type of background here, and then we can come into our fitting model. So I'm going to come down and choose an asymmetric function here. So this is an LA type line shape. You do have the option of a Dunning-Kruger type line shape. These don't tend to work very well with a Shirley background, so we're just going to stick with an LA for now. And we're just going to add a single peak, and this is going to be the first of our nickel metal peaks. But there's clearly a little bit more going on here. We don't just have a single peak, we've got this intensity here. This is caused by plasmon interactions. There's some really great work from Surface Science Western in Canada, Mark Biesinger's group, where they've kind of developed models for all of these transition metals. If you haven't checked out xpsfitting.com already, definitely do. It's an amazing website with lots of great resources from the team at Surface Science Western. Some of the peak models that you can use for things like nickel can be found there, with all of the information that you'll need. That's what I'm using as a basis for this fit. So I've added one peak, and I'm going to go back and just add two more, which are going to represent the bulk and surface plasmons. And I can use the same locking parameters as before. In fact, we can give ourselves a little bit of a fitting grace here. So the first plasmon is 3.7 electron volts above the main peak, and the second is about 6 electron volts above the main peak. And I'm also just going to tell KherveFitting to lock the full width half maximum of those two plasmons to be equal. So now we've got 3 peaks in our system. If we just click on fit, that'll get them roughly in the right place. And now the next thing to do is just going to be to try and do a complete fit of all of our peaks to model that asymmetry. So let's see how close we can get with a large number of fitting iterations. So you can see already these peaks are fitting together quite nicely. I've made a mistake in my locking parameters. So we've got really different peak widths for our two plasmons here, because I have locked C to be equal to itself. So let's just go back and actually lock that to the right peak. And let's just remove that peak and add another one. Add a single peak. A+6. And then we're going to lock this to B. There we go. Now we can try again, fit n number of times. And now this is looking a bit more sensible. This is looking a little bit more like we should be getting. The plasma peaks are a little bit wider than I would expect. If you look at the fittings developed by by Mark and his team, these are a little bit narrow, so I'm just going to add in another alteration here. Let's change these fourth half maxima to be about 2.4, and then we're just going to change the limit so that our upper limit is about 2.8 electron volts wide, and then if we click fit again, it should optimize the asymmetric line shape that we've got there so that our plasmon peaks don't go wider than 2.8 eV, and it looks like we're getting a pretty reasonable fit for those as well. Our RSD is pretty good, and we've got a nice asymmetric function for our nickel. Developing these line shapes can be quite tricky in CASA, so having the ability to use curve fitting to generate the asymmetry parameters for these line shapes is an amazing tool. Even if you carry on using CASA XPS, you can use curve fitting to kind of optimize the asymmetry on these line shapes for your fits and then import that back into CASA XPS. Or you can just use curve fitting for everything. As you can see, it's very straightforward but also very powerful. So that's it for our intro to peak modeling. I hope you found that useful, and definitely check out some of the articles and references that I'll chuck in the description. As always, download curve fitting, just have a play and start getting used to some of these functions. Gwilym's obviously got a lot of reference data in there that you can use to get started, get practices and get training. So definitely jump in and start using some of these tools. And that's it for this week. Hope to see you again soon. Thanks for watching. Goodbye.